Thanks for coming, everyone. My name is Joe Melville. Let's talk deep tech. In its original sense, a frontier is a place that we have not physically explored. There are exactly 3 frontiers. There's space. Everyone loves space. This is a Voyager 1. There's the deep ocean. This is DSV Alvin exploring the wreck of the Titanic. Finally, there's the deep earth. This is a laser drill tank, I guess. We don't really explore the deep earth. In fact, our relationship with the subsurface is exceedingly simple. We take things from it. Coal, oil, iron, uranium. Sometimes we put things down there. Sometimes stuff happens to the things we put down there, and we get a different thing out than we put in. We don't always know why. Chemistry in the subsurface can subvert our surface-dwelling intuitions. Take this reaction. Hydrogen plus carbon dioxide reacts to form methane and water. Well, I'm an electrochemist. I'll tell you what I see. When I look at this reaction, I see hydrogen is an electron source. It's reacting with CO2 as an electron sink. This is a kind of redox reaction. You need both, a source and a sink, to do any sort of chemical redox. Now, we can do this reaction on the surface. It's well known. It's called the Sabatier reaction. And in fact, it's basically the reverse of steam methane reforming, which is how we make 99% of our hydrogen. And that's the exact reason there's almost never any economical reason to do this reaction. Where are you going to get the hydrogen? The subsurface does not work this way. In the subsurface, it's common for reactions with abundant electron sources to be limited by a lack of sufficient electron sinks. This is the complete opposite of the way we are normally used to thinking as surface-dwelling, oxygen-breathing chemists and chemical engineers. This opens the possibility for an entirely new genre of industrial chemistry. We could take abundant electron sinks, like CO2 and nitrogen, and inject them into the subsurface. There, they will be acted upon by high temperatures, high pressures, and an intrinsically reducing chemical environment. Catalyzed by microbial activity in the subsurface, this can produce valuable commodity chemicals, which we can then extract for use in sustainable fuels and renewable materials. Bioreactors are great because they can do complex and selective transformations under fairly mild conditions. But bioreactors are also very slow. But if you start to consider an entire subsurface oil reservoir as its own naturally occurring biogeoreactor, you'll realize it begins to approach or even exceed traditional surface thermochemical reactor rates. It achieves this feat through sheer size, cubic kilometers of reaction volume. Our knowledge of biogeochemistry has been stuck in the past. It's purely reactive, and it's largely siloed within the legacy oil and gas industry. But new industries are drilling into the surface, and there are new technologies for genomics and sequencing, and that means that the time is right for a revolution. We still do not understand the subsurface, even though it's been the dominant source of all of our materials and energy since the Industrial Revolution. I'm proposing a new ARIA opportunity space to unravel the mysteries of life deep within the Earth. Through this, I believe we can make our existing industries more sustainable and even discover entirely new primary resources. Thanks for listening. My name is Joe Melville. If you are intrigued, come see my full talk at the end of the lightning talks. I'll be in the other room, Faraday. Thank you.